Sorry, I guess I was muted.
Yeah.
Okay, great. I just wanted to, we should get started because it's time. I just wanted to say a quick comment about the project presentations, just an overview. Just so you understand where you are going with the project. So your assignment 2 was kind of building the foundation for the rest of the semester, which is where you did the literature review. Assignment 3 is kind of was your innovation. It's kind of, I would think about it like an initial analysis of your innovation. The next assignment, which you're working on, due November 3rd, is more detailed analysis with more data and things like that. And I kind of called it Hack Your Innovation. Assignment 5 is the commercialization aspect of it. It's really how to turn your idea into reality. It's something I meant, just to give you an overview of where you're going at the end of the semester. So hopefully you'll produce something that's fairly substantial. Okay, the other point I want to make is that next Thursday is the midterm, but on Thursday, let's see, on Thursday, here we are, we won't have class. Just to clarify, there is no class, so you don't need to log into Zoom. And the midterm will be posted at a specific time, and you'll be given 24 hours to respond and submit it back. And I'll give you more detailed instructions next Tuesday, but most likely I'll just post it on Canvas, and you can respond. Either you can handwrite the answers, take a picture of it, or scan in PDF, or type it, whatever you want, and submit it back on Canvas. You can submit it on Canvas, you can email it, you can put it on Slack, whatever you want, but you have 24 hours to do it. And again, everything is open, but just not collaborate, discuss with others. Any questions about the midterm? And of course, Section 90 students do not need to do it. Of course, you're welcome to do it, and I recommend it as a practice, but your points for the midterm won't be counted in the grades. Any questions before I move on? None? You can still hear me, right? Someone say yes.
Yeah, we can hear you. Right now it's
good. Okay. Good. Okay, if you don't have questions, we can move on. So today is basically the last lecture before the midterm, because on Tuesday we'll have a review. And review means we'll basically cover what I think are the most important things you need to know for the midterm. So just be aware of it. Also monitor the chess. Okay, great. So you can also bring your questions there and also post out on Slack, as many of you have already done. So today we're going to talk about two topics, statistical ray optics and anti-reflection coatings. Both are quite important, but they are also, at least the statistical ray optics tends to be a little mathematical and a little bit abstract. So hopefully we'll try to make intuitive sense of it. And just on the onset, I just want to say that I will not ask you any of the mathematics related to today's lecture in the midterm, but I will expect you to know the intuition, okay? So you won't have to derive any of the equations and so on. Just it's a caveat. And after the midterm is approximately halfway through the semester. So, and the rest of it's, okay, there, and we'll talk about that later. So let's jump right into this statistical ray optics. Now, while it's loading, I just want to point out that most of this lecture is based on a particular paper that is posted on the class website, so you can look at it along with the notes. This is a paper written by Eli Yablonovich, who at the time was at, I believe, at either Bell Labs or GE Research, or one of those places, but today he's at Berkeley. He's a fairly well-known person. He's been nominated for the Nobel Prize in Physics and so on. Really sharp guy. I know him personally as well. So he developed this theory to understand the geometrical optics for complex random surface shapes. So far we've talked about geometrical optics in a very deterministic sense. What does that mean? That means we've talked about spherical surfaces. Okay, we said, okay, ray comes in, at this location, because it's 90 degrees, there's nothing, no refraction. But here, because of Snell's law, there's some refraction happens, right? Something like that. Now, the question is that he was trying to answer is, what happens if I had a surface which was completely random? Can I say something about the geometrical optics properties of such a surface from a statistical perspective? Of course, randomness is a statistical concept, right? So of course, you can, of course, go deep, zoom in and do Snell's law at each surface. But the question was a little more general than that. The question is, what is the overall averaged or statistically average behavior of light when it encounters such a surface? And this is technologically quite important, as you will see shortly. So that is the goal of this lecture and the goal of that paper, which you need to read, by the way. Okay, so let's talk about some of the basics. Now, before I jump, actually, I thought I had okay, before I jump into the basics, I want to explain why we're learning this, okay? This might seem kind of random for you, right? Because you're talking about random structures. Now, there is a very important reason we're learning this. If you take any solar cell, any advanced solar cell today, it has an absorber, and you will learn more about the physics of this the week after next. But above the absorber, you have essentially a random textured surface. And the reason for this is to ensure that light that comes in is trapped inside the absorber as much as possible. Okay? And this is almost ubiquitous in all the advanced solar panels today. So we need to understand the physics of this a little bit. And that's the goal for studying the math. Okay? So people, including yourselves, can design, understand why it's here, and also how to improve it. Okay? So that's the goal. That's the motivation. So let's jump right in. Let's think of, and everything comes from thermodynamics, fairly from a fundamental perspective. Let's imagine a surface. Okay? So this is a surface. It's a transparent sheet. Sheet means it's a relatively thin object, and let's say it's bathed in some black body radiation. Okay, so sunlight, for example, right? And it has a refractive index which is changing with position, as noted here, n of x. Under thermal equilibrium, we know that its temperature will be constant. It's not going to change with time. That's what the definition of equilibrium is. Now, from quantum theory, we can actually derive what is the energy density of electromagnetic modes inside this medium. Okay, you don't need to know how it's derived, but it comes from something called the Planck formula. And the only thing I want you to know about this is, well, first of all, I'll point out a few things. First of all, it's dependent in an exponential sense on temperature. Of course, it also depends on frequency, which we know, right? For the energy of a photon depends on frequency, that's omega. And it depends on a few other things which we're going to ignore. K, for example, is called the wave vector. This is wave vector depends on frequency. Now, what's important is the second equation here, which is the intensity of light inside this material. And it's simply given by the density of electromagnetic energy multiplied by something called the group velocity. Again, you don't need to know exactly where this comes from, but the important thing is on this equation here, this part right here, okay? The intensity inside the material can be shown to be n squared times the intensity outside the material. But here, it's air or vacuum, so n equals 1, okay? That means if I have intensity of light I naught outside the material, theoretically, I can have intensity inside the material n squared times, okay? Which is a big deal because n, for instance, in silicon or glass, for instance, 1.5, so n squared becomes 2.25, right? So that's increasing the intensity by over 2x. So that's a pretty big number. So this situation is only valid when we have light rays that are called ergodic. Now, what does that mean? This means that light rays, once it enters the medium, forgets where and in which direction it came from. This creates what is called statistical randomness. So now you can see, so this requirement is the reason to put, if you have your solar cell, the surface of the solar cell is textured, because you're trying to create the statistical randomness in order to gain this n squared value driven by the math. So let's dig into this a little bit more. So again, just to reiterate, the intensity within a medium in thermal equilibrium with the black body radiation is n squared times higher than the environment. Okay, so now let's think about in some more specific detail. Okay, light's coming in. Let's say this is direct sunlight coming in at some specific angle, right? Sun is in some direction. Once it enters this medium, light essentially will be randomized because it bounces around. Of course, because this surface here has some random shape, it will of course undergo Snell's law. And then here, some of it's reflected, some of it actually passes through, right? And so on and so forth. And because the shapes are very random, this will bounce around at many different angles. And after a couple of bounces, this ray does not know where it came from, or it's very difficult statistically average, in the statistical average sense, for us to figure out where that particular ray came from. And that's the definition of ergodicity. Okay, they forget their initial direction. After one or two reflections, it is statistically averaged over some area of interest. So that's the assumption. Now, you can also do something clever by putting a white reflective surface behind the this textured medium, such that light bounces around, right? Bounces around many times, and so on. Some of it, of course, escapes, but it can come back in if we put a reflector surface here. And because it can come back in, you get a 2x increase in bounces, essentially. And this 2 also comes into the equation here. So you get a 2n squared increase by putting a reflector at the bottom. Okay, so far so good. So for example, if you want to make a very efficient solar cell, so you want to not just have the solar cell and not just this texture, but you also want to have a reflector at the bottom. So you allow the light to bounce around inside the solar cell. The more times it bounces around inside the solar cell, it has more chances of it being absorbed to create electric current. That's the intuitive picture. Now, a few caveats. This is only true for optically thick films. I told you that the film is thin before, but the principle we've talked about ignores something called physical optics or diffraction. So this is only true when the thickness of the film is larger than lambda over 2n, where n is the refractive index. But that's already a pretty small number. For instance, if you take a wavelength of 1 micron and a refractive index of 3.5, for instance, silicon solar cell, for instance, the smallest thickness is simply 1 micron divided by 7, right? So it's a pretty small number. What is that? 1,000 by 7. So anyway, that's like less than 100 little more than 100 nanometers, right? Something in the order of 100 to 200 nanometers. So it's pretty thin already. And how much enhancement in intensity is possible? We just said, if you have the reflector, there's 2 n squared. Now n is 3.5, right? So 2 times 3.5 squared. It's a pretty big number, right? Something like 10. 3.5 is about 9. Oh, sorry, something like 20. So 2 times that, something in that order. So that's a pretty big enhancement. So it's worth doing, basically. Yeah, a couple of things also to keep in mind about the statistical behavior. If you have high levels of symmetry, for instance, if you look at an analogy of a billiards table, If you have a very high symmetry, so it's a rectangle, the rays of light, if it bounces around inside this rectangle, can only access 2 angles. If you have a square, you can actually only access 1 angle, and so on and so forth. So the number of angles accessible in a rectangular table, because of the high symmetry, is only 2. So this is not ergodic. To make it ergodic, you need to have more complex shape like a polygon, which is why that texturing is important, as we saw before. Also, a caveat is that light is, of course, not like billiard balls, because the systems are not closed. Light has to enter the system and escapes the system because of a critical angle, right? So in other words, if you have air here and silicon here, whose refractive index is greater than 1, of course, and light comes in at an angle, if this angle is larger than the critical angle, we know that it will be trapped. But if this angle is smaller than the critical angle, we know that it will refract out. This is escaped, right? So it's not a closed system. Light can still escape. So we need to account for that. And the critical angle, as from Snell's law, we know it's given by 1 over n. So this is the critical angle. So if I have light, so imagine an LED where light is emitted. We're talking about the opposite, but imagine light is emitted in this region right here. It is emitted in all directions, but the rays of light that are larger than the critical angle, of course, are trapped, as shown here, right? Trapped in this material whose index is greater than 1. Let's imagine that's 1, that's air. But this ray, for instance, is within the critical angle and it escapes. So this is a loss. And of course, you can have the loss at the bottom as well, right? Depending upon the refractive index of the substrate, but you can also have loss here. Okay, so there is a code of angles defined here within which light is lost, and that's defined by the critical angle. And by converting that cone into a solid angle, you can actually calculate the probability that the light is trapped or the light is escaped. And to convert to a solid angle is pretty simple, approximately anyway. It's because for small thetas, you can approximate the solid angle as 4 pi is the whole sphere divided by 2n squared, where 1 over n is the critical angle. Now this 2 comes because there are 2 sides to it, 2 cones, one on the top and one on the bottom. So the probability that a light ray inside a medium will escape is small. Even with a small amount of randomness is enough to create the ergodic behavior we talked about before. Now we can put all this together into an equation to understand how much of the light is actually trapped within this film that we're talking about. So first of all, let's imagine a situation where light's coming in. So that's the incident light, and it is refracting with Snell's law, as shown there. And we're going to assume some transmission efficiency of T incident, T-I-N-C. Let's ignore this phi for now, but you can see that that's this incident angle right here, okay? And then we're also going to consider this little infinitesimal area of the surface. Now, the idea is to understand, okay, how much light came into the system, how much light escapes the system, and under thermal equilibrium conditions, because temperature cannot change, whatever came in must match whatever escapes, and this is called the detail balance. And this is something I shouldn't say recall because you haven't learned it yet. You will see this on the lecture on solar cells. So keep this term in mind, detail balance, which just means you're balancing what comes in to what goes out. In this case, we're simply thinking about this film or the surface, but in the case of the solar cells, it's a little more complicated. So let's work out the equations a little bit. The intensity inside the film, which means this region here, is given by some, we're going to assume it's isotropic, which means it's equal in all directions. It's given by this integral, B internal intensity, which is this internal intensity per unit solid angle, multiplied by cos theta d omega. Now cos theta comes from the fact that you have this angle which projects this area dA So if I take this dA and project it normal to this ray, this gives me cos theta. So because the ray that's normal to the device is the part of the ray that's absorbed. And we'll see, we saw this in the case of the Lambertian emitter. It's a very similar situation here as well. And then we can do the integral from 0 to 90 degrees because you only have to do one side. It's symmetric, multiply by 2 pi. Because you're converting the solid angle into a one-dimensional angle. So relatively simple trigonometry here, I won't go through it. The factor 2 here comes from the extra pass because of the reflective back surface. And this integral can be worked out. It's pretty simple. Cos theta sine theta is sine 2 theta over 2, and the integral is simple. It becomes half. So you get I int becomes 2 pi times b int. So relatively simple expression here. That's the intensity inside the material. The intensity of light that escapes is the exact same expression, but now you're doing the integral from 0 to the critical angle. And then you also have a special thing called T escape here, which is simply the probability that light actually escapes. And then we make some simplified assumptions where this is independent of angle. So here you have theta, but we're going to drop that. And then you get some angle averaged escape transmission. You get another simple expression here. And then you're gonna match them. Again, you don't need to know how to derive these, but I just want you to understand these things conceptually. The tail balance means light comes in is equal to the light goes out. So light coming in is simply internal multiplied by the incident intensity multiplied by the transmission. That should match the internal intensity multiplied by the loss that escapes. Okay. So what's important here is that now you get a very simple expression where the intensity inside the material is 2n squared times the intensity outside the material. Let's ignore this, well, approximately. Now, if we don't ignore this, you see something interesting is that by playing with this factor, you can actually get more than 2n squared as well. But let's not worry about that for the sake of this class. Just be aware it can be done. And there are some very interesting things people have actually done taking advantage of that. But like we're going to ignore this for the purpose of this class, and we'll just get back to what we said a few slides ago. Intensity inside the material is 2n squared times intensity outside the material. And of course, this factor 2 comes from the fact that we have a reflector behind this film. Now, yeah, let's ignore this last point here because we haven't talked about the brightness theorem. Now, let's think about why are we talking about all this. At the very beginning, I told you this is because we want to try to trap light inside the solar cell more efficiently. So let's talk about this a bit more. This is shown pictorially here. So if you have a very smooth piece of glass, light comes in, it refracts and it passes out. And one interesting thing, of course, is that this ray is now parallel to this ray. So all that has happened is that you've displaced the rays, right? That's all that has happened. So you don't trap, you have one pass here. If you put a reflector or a mirror down here, you have two passes, right? Light comes down, bounces off, and goes away. Now, if you put a mirror and some texturing at the top, you can have more than two passes. So that's actually pretty good. But you can do even better. You can put a mirror and even very complex texturing on top, and you can get many more than two. And you can do texturing at the top and the bottom, then you can do even larger than two. Okay, so this is the idea. Now you can see the rays are bouncing around lots of times. And the reason you want this to bounce around lots of times is that imagine this is our silicon that absorbs the light. The more times the rays bounce around in the silicon, the more chances it will get absorbed and you will get current from it. That's what you're trying to do. The other thing you're trying to do is that by allowing the light to bounce around many times, you can make the silicon very thin. That has many advantages. For instance, you can make it flexible. Because it's thin, you can use less of the material, so it can be cheaper. Because it's thin, you can potentially make it transparent, so you can actually see through a solar cell. So lots and lots of very clever, interesting things we can possible. So that's why we're talking about this whole idea. And this is what it looks like. So if you open up a solar cell, for instance, this is what you'll see. This is under an electron microscope, so these textures are very, very, very small. They can be random or they can be somewhat ordered, as shown on the right-hand side. And the procedure for manufacturing these are fairly complex, but relatively mature as well. So it's done in large volume production today. So as I said before, why are we talking about light trapping? Because we can use thinner cells. This allows it to be cheaper, flexible, etc. It also has, because you can, if you use thinner cells, you could have higher quality materials, higher quality of the silicon, which means that you have fewer defects and less losses. The carrier recombination is something we'll talk about in a couple of weeks. One thing we haven't talked about so far is absorption. So in all the analysis, for instance, when we did this detailed balance analysis here, there was no absorption. Light was just passing in and out of the system. Once we add absorption, it includes an extra term, and you also have to account for the area that we are thinking about, that term there. It's the same as this term here. Light can get absorbed at the interface, which is this term here. I won't go through the math, but you have this efficiency of absorption, which is also called the fractional absorption. Light is absorbed in the bulk. This is the important absorption that we are interested in, because this gets converted into energy, usable energy, okay? So that depends, works out to be an integral, but the important thing, and I won't go through the integral, the important thing are these two terms here. Alpha, which is the absorption coefficient of the material, silicon for instance, and the thickness, L. So of course, the thicker the material, the more you'll absorb. Everything else is just some parameters. They're not simply too important. This is just the area, and this is the intensity that we talked about. Now we can apply detailed balance, light in equals light out. So this is light coming in, that is light escaping, this is absorption at the interface, because remember the eta. This is absorption in the bulk, remember the alpha L. You can equate all this, and there was a typo that's corrected there, so you get this expression for the internal intensity. The goal is to increase absorption in the solar cell. The absorption is actually given by this expression. So now you can see how much of the light is actually absorbed and how do you maximize it. So if you think about the efficiency of absorption, which is a fraction of incoming light that is absorbed in the bulk, is given by this expression here. Now let's look at this expression. What can you do to increase this? You can use the material that has high absorption, alpha. You can increase the thickness of the material. You can make it more transparent so more light gets in. You can reduce the loss, right? That's this. You can reduce the reflection losses, which is not useful. Of course, this, by the way, the alpha L also appears in the denominator, so that's kind of a more complex thing we have to think about. But one thing you can also do is this 2n squared. You can increase that with the refractive index. Now let's make some simplifications. Consider the case of weak absorption. For instance, silicon is an indirect bandgap semiconductor, which we will talk about in 2 weeks. So let's put that aside for the time being. It just means for the purposes alpha is small. Let's also assume that eta is small. So in other words, that the interfaces, there's very little absorption. So let's also ignore this T escape, T incident. Let's make them equal. So in this equation, these things essentially cancel out, this and this. Yeah. And the maximum absorption, if you do all that, what you end up with, let me see. Yeah, and the A's, let's ignore this, cancel these things out. Yeah, these things cancel out, and the maximum absorption then becomes 2 times 2n squared. Because you can see it becomes, let me write that down, 2 alpha L divided by, let's see, the T's cancel out. 1 over 2n squared, eta is ignored, plus 2 alpha L. So assume that n squared is much larger than alpha L, this just becomes 2n squared times 2 alpha L. Okay, I'm just ignoring this because this number is much larger than this number. So what you end up with, the maximum absorption you can get is 4n squared. And that's a pretty big number, right? Because if n for silicon is 3.5 squared, you know, something like 9 or 10, 4 times that is about 40, right? That's a huge number. So it's worth doing it. Now, in that paper, they actually did the measurements, and the measurements are useful to think about so you understand what does this mean in practice. So here we have a silicon wafer, which is in place for the solar cell, a reflective surface behind it, and light is coming in from the top. And there's something called an integrating sphere, which measures the light that comes back. So light comes in, bounces around, and something comes back. And what coming back is the loss. Now, if you measure it, this is what you see. You can measure two things. One is measure with a perfectly flat, unpolished silicon wafer, and you get the top curve. And if you texture the surface, you get the bottom curve. So you can see that the reflected light, also called the backscattered light, is decreasing, which means that more light is absorbed in the solar cell. You also see this interesting shift in the absorption peak, which is actually very important to control the band gap of the solar cell, which we will talk about when we talk about solar cells. And the dashed line is just the simulated or theoretical prediction, and the solid lines of the experiments. They agree quite well. Now, there's a different way to implement this whole principle with to minimize the amount of silicon that's used. Now, silicon can be made into granules, shown by these circular entities here, and they can be embedded into a plastic sheet. PMMA is plexiglass, essentially. Polymethyl methacrylate. Now, if you put this and the white backing is the reflector, you can get a very similar sort of effect where light comes in, it bounces around in this PMMA, which is a transparent film like plexiglass, and gets trapped in it and get absorbed by the silicon. So as shown by this ray. Now, I won't go through all the math here, but you can prove, in the interest of time, I'm going to go through this quickly. You can prove that the intensity inside the PMMA is higher than the intensity in air, and the absorption in the silicon is much larger than what one would expect from the area fraction of the silicon. So which is shown in this plot. So again, it's the same experiment as before. It's looking at the backscattered light. So if you don't have the silicon granules, just a film of PMMA, you get most of the light is simply reflected back because it's a mirror behind it, right? So you have a film, and then you have a mirror behind it. Light passes through and comes straight back. Now, once you have this little balls of silicon, and you put a mirror, you get light comes in, some of it's trapped, absorbed, some of it's bouncing that way, comes back, trapped, absorbed, a little bit comes out. So you can see what comes out is measured here. This is very high, 100% reflected back, very low here. So this difference is what's absorbed and can be potentially converted to useful energy. Okay. Now, one nice thing is that because you're only using a little bit of silicon here, where high quality silicon can be expensive, such a solar cell can be very cheap. And of course, because it's a thin film of plexiglass, it can be very flexible as well. So that was the idea for this. Okay, and that's basically all I want you to know. Again, I'm going to stop here for a second so you can have a breather, but let me summarize. We thought about two important things. One is why by texturing a surface, you can essentially trap more light, and that's useful for solar cells. Two, we figured out how to analyze such complex structures because it's texturing is randoms. How do you think about it? You have to think about it statistically. We can apply this principle called detail balance to analyze these structures, and essentially we proved that you can get absorptions increase as much as something like 2n squared. Okay, so those are the two conceptual things I want you to get out of this part of the lecture. So I'm going to stop and see if there are any questions. And you don't need to know how to do the derivations, but at least you need to know conceptually what we talked about. And let me just, while we take a short break, I just want to point out the paper is here, and I highly recommend you to read it. Yeah. So, oh yeah, he was an Exxon research engineering. So, yeah, so you can go through this. It's a relatively easy read. There's a little bit of math, but otherwise it's a relatively easy read. Okay, the second part of the lecture, I want to talk about anti-reflection coatings, but maybe I should let you, well, yeah, I guess we can. Right in. We might finish a little early today, but if you have questions, I'm happy to answer them. Now, the reason we are talking about statistical ray optics and anti-reflection coatings in a single lecture is because they're related, as you will see. Anti-reflection coatings are, of course, technologically very important, right? For those of you who wear glasses, you're probably very familiar with this. You can pay some extra money and get anti-reflection coatings on your glasses, so you have more light coming through, less light reflected, right? Less glare and things like that. So these are very important, right? So what is anti-reflection? So for those of you wearing glasses, here's a good example where on the left-hand side, there is no anti-reflection coating. Right-hand side has the anti-reflection coating. Of course, it looks not so good, not so aesthetically pleasing. And the fact that you're seeing the reflection on the left-hand side also means that the person wearing the glasses is seeing less light coming through. So this can be very problematic, especially if you're driving and things like that. Of course, here are more examples. So, if you're looking through, if you're the user, you can see the anti-reflection coating is much better. It can also, yeah, you can see the examples here. And you can also reduce the glare and things like that. So, now, what does that mean? What is anti-reflection coating? It means if you have 100% light coming through, if you have anti-reflection coating, very little light is, very little light is reflected at 0%. All of its 100% goes through. However, if you don't have anti-reflection coating, if this is glass, up to 4% or so or more reflects. So only 96% makes it. Okay. So that's sometimes a problem. And you can imagine if this is a solar cell, solar cells have to have a glass cover on top to protect them. If you're losing 4% of the light from the top, that's not so good, right? Because you already lost it. Especially, it's much more when you try to integrate over all the angles and so on. So this is why we want to learn about anti-reflection coatings, try to figure out how to minimize this loss. Okay, we already saw that, so we already saw that. Now, there are many ways to create anti-reflection coatings. The first approach I want to talk about is quarter wave coatings. Now, quarter wave coatings depend on something called interference. So let me play a quick video on what interference means. So interference is wave theory of light, which we haven't really talked about, but let me just play this first and we'll talk briefly.
That the two mechanical waves of the same frequency can interfere constructively if peaks of these waves are traveling in phase, and destructively interfere if the waves are not in phase. Similarly, light waves also interfere. Light waves
So I'm going to stop,
interfere
pause here for a second.
if the waves
Oops. So here you can see a picture where on the top you have two waves that are in phase, and they add them, you add up, you get twice the amplitude on the right-hand side. The bottom, we have a situation where the two waves are out of phase, so the peak of one wave corresponds to the minimum of the other wave. They cancel out when you add them up, and the intensity of the sum, the amplitude of the sum is 0. And this is the basic idea. And of course, let me keep playing this.
Are not
You've
in
learned
phase.
this in high school
Similarly,
physics.
light waves also interfere with each other as shown here. Light waves interfere only when the electromagnetic fields that constitute the individual waves combine. The interference pattern thus obtained contains alternate zones of maximum and minimum intensity called fringes. But if two light bulbs are placed side by side, no interference effects are observed because the light waves from one bulb are emitted independently of those from the other bulb. That is, they are not in phase. Thus, interference of light is the phenomenon of the non-uniform distribution of resultant intensity when two light waves from two coherent sources superimpose on each other. Thomas Young first demonstrated the interference of light in 1801.
Stop. So let's go back to our notes here. So why is this important for us? It's important for us if you think about this situation here. So imagine this is air. Okay, that's index is 1. This is, let's call it some plastic. Let's call it PMMA. And let's call this some other material like silicon. Okay. So light comes in. Let's look at this ray A. Light comes in. Some of it's reflected from the top, as shown here. We're trying to minimize that. And let's think about another ray B, where light passes through and it's reflecting from the bottom. Now, what we want to do is we want to design this structure such that this ray here interferes destructively with this ray here, because that means that no light will reflect back. Okay, so you want rays A and B such that they're out of phase by λ/2 or pi and destructively interfere. And you can think about, okay, what does this D have to be? So since we haven't studied physical optics, I guess I should just walk her through. So D will have to be, so the light B, ray B is going through one D this way and another D this way, right? So ray B has gone through 2D while A has gone through 0, right? Just reflects right from the surface. So the difference in path length between B and A is 2D. Okay, that's the difference between the rays. Now we want this to be equal to half the wavelength, right? Then they will destructively interfere. So in other words, we want this ray, this to be look like that, and this will be A, and then we want B to look like that. That's B. So they'll cancel out. So in other words, we want this to be shifted from this by λ/2. So that gives me of course, we also have to account for this refractive index here. So this lambda actually is the wavelength inside this medium, right? So that means we also have to write 2D is lambda in air, let's call it λ0, divided by 2 times n, because n prime, sorry. Refractive index, the wavelength inside the medium is reduced by n prime. So now you get the value for D should be λ0 divided by 4 times n prime. So that's what you need to do. So that's a very simple example of a anti-reflection coating. Now, as you can tell, this only works when you have a single wavelength of light, right? It's dependent on λ0. And you can also tell it will vary if I change the angle. In other words, if this ray comes in at a different angle, it has to bend. The amount of distance it travels will change, right? You can calculate it, but it will vary. So a single thickness here will only work for one angle and one wavelength. So that's very restrictive. And that's shown in this plot. It depends upon wavelength and angle. This is reflection. It's a function of wavelength. So at this location here, the reflection is 0. So it's a perfect anti-reflection coating. But if I go away in wavelength, the reflection increases. Yeah, so this is example of silicon under glass with optimal anti-reflection coating. And this is bare silicon, it reflects quite a bit. This is just with glass, no anti-reflection coating. And also the angle is important. As I said before, if you come in at a small angle, small amount of light is reflected. If you have a large angle, large amount of light is reflected. This is a very easy experiment to do. You can go to a window in your house and look straight on. Of course, you can see through very easily, but look at it at a very steep angle, you will see that it acts like a mirror. You will see what's inside the room, right? And that's what's shown in this plot here. The reflectance actually increases with the angle of incidence. So it's a big problem, right? You don't want this to happen. For instance, if you put solar panels on your roof and the sun is straight ahead, it's perfectly fine. But you also want it to work when the sun is not straight ahead, right? As much as possible. So how do you solve this? You want to build an anti-reflection coating that will work for all angles and all wavelengths. Excuse me. This is conceptually somewhat easy to understand, because what you're trying to do is you're trying to do a little bit of an impedance matching problem. Because if you look outside in air, the refractive index is 1. In silicon, the refractive index is very high, 3.5. And that's the reason why you get these reflections, because the impedance that the light sees is very high for silicon. So you can put some material here that slows down the variation of refractive index. So if you pick a material like silicon nitride, whose refractive index is a bit larger than 1, but less than silicon, 3.5, that will essentially act like a buffer, preventing more light from being reflected. And this can be done such that it's somewhat independent of angle. Yeah, that's one of the ideas. This example is just to show the influence of angle to design this in the case of quarter wave plate. So I'm going to skip that, not so important. I want to talk about this, which is the matching the index. You can also do something pretty clever, like you can take so silicon, this is there. You can grade the index. You can go from high index and decrease the index. If I were to plot n, it's a function of this thickness, you come from very low value, which is 1, to some high value, which is 3.5 for silicon. So you can grade the index slowly so the light comes in. And such an approach is actually incoherent, which means that it doesn't need to, it can be fairly insensitive to both angle and to wavelength. Now, I want you to, I'm not going to put you in breakout rooms, but I want you to think for like 30 seconds or so and think about, are there other ways to achieve the same effect? Think about other possibilities of trying to do this impedance matching. Any ideas? None? So think about the fact that you're making this graded index. You can potentially also make this graded index based on geometry. So imagine you had a conical shape, which is made of high index material. You go from the top, and if I take a cross section here, I'm increasing the fraction of the material that remains in the high index. Imagine I make a periodic array of these. So this will be another example. So I'm going from index of 1, and simply by increasing the fraction of the material as I go down, I'm increasing the index. So this is easier to do because I can work with just one material and simply etch it down or machine it, right? Whereas in this example, I have to make different materials with different indices and so on. And that's much harder to do. And this is actually what's done, for instance, in solar cells. So this is an example of a work, I believe, from Harvard, where they grew these kinds of structures on top of silicon. Okay, and because you get this kind of index variation as you go down, going from air all the way to silicon, you can trap light, and you can see the wafer looks black. It absorbs the light. Now, close to 100%. This reflects something like 30%, like a mirror, right? And the only difference between these two is that this has these grass structures, and this is simply polished. So you can see it can have very dramatic effect. And then that means if you can absorb most of the light, that means it's a great solar cell, for example. Or it can be a great solar absorber for a hot water system or a desalination system or whatever, right? And you can, of course, also engineer this more carefully. For instance, by designing these geometries in very specific ways, you can change the color of the surface as well, how much light is reflected. So these are all very interesting things that are actually happening in research and industry today. So this is an example of the black silicon. Okay, skip. Now, we can also spend a little time analyzing this a little more quantitatively, okay? So what does that mean? That means we want to think about a situation like this. So air, PMMA, and then silicon. Now look at the structure, the interface between PMMA and silicon is textured to essentially trap the light. So which is shown in this example. Light ray comes in, some of it passes through, some of it's reflected off, and is trapped. Again, we can do the analysis, similar analysis as before. T incident is the transmission from air to PMMA. Eta is the absorption factor at the rear surface, which is here. And the reflected light is T incident times 1 minus eta, which is, so in other words, 1 is here, T incident is here, 1 minus eta times T incident is here, T incident times eta is here, and so on and so forth, right? It keeps bouncing around, so it becomes a geometric series. You can write this down. You can calculate the absorption at each reflection event and add these up. So you can see, let's do this very carefully. So the first absorption event is here, it's T incident times eta. The second reflection happens here, which gives me 1 minus eta, because again, I'm going to write these down. This is 1. This is T incident. This is 1 minus eta times T incident. That's this part times the probability of the fact that it's trapped. It's 1 minus the escape probability, which we calculated before, is T escape divided by 2n squared. And so on and so forth. So then the second absorption happens here. You multiply that by eta times whatever came back, and so on and so forth. And if you add all these terms up, first absorption, second absorption, and so on and so forth, you'll see it forms a geometric series, as shown. And this is a proxy for how much light is absorbed in the silicon, because this eta includes everything, basically, because it's going down into the silicon. So you sum them all up, it's a relatively simple geometric series, and you come up with an expression which looks like this. Okay. And we can now plug in the numbers. So let's imagine refractive index of PMMA is 1.5, so it's plexiglass. Refractive index of silicon is 3.5. Eta is the Fresnel reflection losses, which is given by this expression here. It turns out to be about 84%. Incident transmission through the glass is 96%. Remember, I told you reflected off. So 96% from glass. PMMA and glass have the same index, so it works out to be roughly the same. Again, we make this assumption, same as before, and we get an absorption of 92.3%, which is quite good. So again, what we want to understand is that if we do nothing, what do we get? We get 84%. By simply putting PMMA, texturing the surface and putting PMMA on top, you get an increase of absorption of about 92.3%. That's a pretty significant increase. Just to summarize it, 90% of the light gets absorbed in the silicon and the PMMA silicon interface. So about 10% of the light is reflected back. So PMMA on top of the randomly textured silicon acts as a decent anti-reflection coating. It's the ARC. If there was no PMMA or texturing, then the reflectivity of a polished silicon wafer is about 31%. So that's a pretty significant improvement, right? Went from, so my comparison before was not quite correct. We went from 31% to 90%. Sorry, that's not the correct comparison either. And from 31% to 10%, you want to reduce it. That's the reflectivity. You want it to be a 0, right? Because you're trying to reduce the reflection. Now you can also think about simple index matching, no need for texturing. So imagine an ARC on a polished silicon. So silicon is 3.5, air is 1. We know that if you pick a refractive index of some material which is greater than 1 and less than 3.5, that can also work as an anti-reflection coating. And we can calculate, do some simple calculations to understand how much can that work. And let's just take the arithmetic mean as the refractive index of the ARC. So it's between 1 and 3.5, pick 2.25. Reflection on the top surface is the index of the ARC minus 1 by index of the ARC plus 1. This gives me about 15% of the light's reflected. From the bottom surface, I have to look at the difference in the refractive index between the silicon and the ARC, and silicon plus the ARC. I get 7.4%. And I can approximately add them up to get the total reflection to be about 22%. So you can see, if I just use an ARC, I get a reflection loss of 22%. If I use so this is only ARC. Now, if I use ARC plus texturing, I get a loss of something like 10%. So you can compare the improvements and see if it's worth doing it. Just to summarize again, the PMMA plus texturing proves to be an effective ARC due to effective light trapping, reflectivity about 10%. All the solar cells are encapsulated in glass protection from the elements, so there is always a reflectivity of 4% of the top. So going from 11 to reducing this to about 11% is pretty good, since 4% is best one can hope to achieve. Again, just to explain, what does this mean? If you do nothing, silicon is like a mirror. Something like 30% goes out. That's nothing. Now, if you put an ARC, you can reduce this to, what do we say, 22%. And if you put texturing and ARC, you can reduce this to about 10%. You can, because we have glass on top, and if you absolutely do nothing, you will still get 4% loss from the glass. Okay, so those are 4 different situations. So really what you do is you put the glass, you put the ARC, which is usually silicon nitride, and then you texture it. I will talk more about this in the lecture on solar cells. And that's basically all I wanted to say today. So we're going to end a little bit early. So if there are, I'm going to stop and see if there are any questions first. I'm going to end early. That way you have a little more time to study for exams and also work on your assignments. Any questions before I stop? I'll go back to the. Just remember that the midterm will cover everything up to today. But again, I don't expect you to do any mathematical derivations. It will be highly intuition based. So you need to have some good understanding of the material. Okay, imaging optics, non-imaging optics, geometrical optics, a little bit of thermodynamics, radiometry, photometry, all that stuff. And you can look at the midterm review for some ideas on what materials to review. Okay, there are no more questions. I guess I'll stop here.
Thank you.
Thank you. And again, I encourage everyone to
Thank you.
post your questions on